Today we are going to be talking about graphing exponential functions. By the end of this video, you should be able to graph exponential functions, and you should be able to identify characteristics of exponential functions. First, an exponential function with a base a is a function of the form f of x equals a to the x, where a is greater than 0, but not equal to 1, and x is any real number. So first, we're going to take a look at how the base affects the graph. So we have 4 different exponential functions that we are going to look at. We have 2 to the x, 4 to the x, 1/2 to the x, and 1/4 to the x. So we're going to start by making some t-charts. When I'm making this t-chart, I'm going to start with the x values, -1, 0, 1, and 2. If I plug these x values into this exponential function, 2 to the x, 2 to the -1 power is 1/2, 2 to the 0 power is 1, 2 to the 1 power is 2, and 2 squared is 4. So I'm going to go ahead and plot those points on my graph. If I wanted to, I could go ahead and look at the x value of 3. 2 cubed is 8, so I could add another point in here. If I continued with some more negative x values, I would just get smaller and smaller fractions that get closer and closer to 0. So my graph for 2 to the x looks like this. If I look at 4 to the x, 4 to the -1 is 1/4, 4 to the 0 is 1, 4 to the 1 is 4, and 4 squared is 16. So if I plot these points, I have, and then 16 is off my graph. My graph looks like this. So if we write down the characteristics of these functions, because they are very similar in their characteristics, our domain for every exponential function is going to be all real numbers. You can pick any number for x, plug it in, or if you prefer to look at the graph will continue to go to the left, and in this case we'll get closer and closer to the x-axis, and as you go to the right, it will continue to get larger. Our range is 0 to infinity. We do not have an x-intercept. We do have a y-intercept at 0, 1. Both of these graphs are increasing. We do not have a vertical asymptote, but we do have a horizontal asymptote at y equals 0. Then for our end behavior, as x approaches negative infinity, both f of x and g of x approach 0, and as x approaches positive infinity, both f of x and g of x approach positive infinity. If you look a little bit closer at the graph, the only thing about this graph that changes when we change the base is how fast the graph increases. When we have a larger base, like this blue graph of y equals 4 to the x, our graph is steeper, whereas the red curve, y equals 2 to the x, is not quite as steep. Let's see what happens when we have bases of 1/2 and 1/4. I'm going to make another t-chart. This time I'm going to pick x values, -2, -1, 0, and +1. If I look at y equals 1/2 to the x, 1/2 to the -2 power is 4, 1/2 to the -1 power is 2, 1/2 to the 0 is 1, and 1/2 to the 1 is 1/2. So if I graph these, if I wanted to, I could look at an x value of -3, and that would give me 8. I can go ahead and sketch in this curve. If I look at y equals 1/4 to the x, 1/4 to the -2 power is 16, 1/4 to the -1 power is 4, 1/4 to the 0 is 1, 1/4 to the 1 is 1/4. Obviously 16 is off my graph. And there I have my curve. So if we look at the characteristics for these two functions, both of them have a domain of all real numbers. They still have a range of 0 to infinity. They do not have x-intercepts, but their y-intercepts are 0, 1. The main difference between these two graphs and our previous two graphs are that these two are decreasing. We have no vertical asymptote, but we do have a horizontal asymptote at y equals 0. And our end behavior, as x approaches negative infinity, both h of x and k of x approach positive infinity. And as x approaches positive infinity, both h of x and k of x approach 0. Again, the base affects how steep the graphs are. And if we compare f of x and g of x with h of x and k of x, we can see that when the base is between 0 and 1, like h of x and k of x, we end up with decreasing graphs, or exponential decay. When the base is greater than 1, like f of x and g of x, we have increasing graphs, or exponential growth. So let's go ahead and look at a couple more graphs. The general form for an exponential function is a times b to the x minus h plus k. You should have seen this in Algebra 2. We have the same transformation rules as we did in Algebra 2. A is going to stretch the graph. The point hk tells you where your starting point is, and then the base, as we just saw, affects how steep your graph is. All of our graphs that we're going to look at have a base of 3, so I'm just going to go ahead and write out our t-chart for 3 to the x. A good rule of thumb is to use -1, 0, and 1 as your x values. Depending on the base or the size of your graph, it might be helpful to also add -2 and +2, but it just depends. So 3 to the negative 1 is 1/3, 3 to the 0 is 1, and 3 to the 1 is 3. So this is going to be our parent graph for the next 4 examples. So if we look at our first example here, we have a of x equals 3 to the x plus 1. This means that our h, k values are -1 and 0. So that means that -1, 0 is going to be our starting point. And I'm going to put a little box here because that point is not actually on the graph, but it tells us how our graph has shifted. So the easiest way to graph these functions, in my opinion, is to treat this hk point as your new 0, 0. So instead of graphing the point -1, 1/3, you are going to graph from this box -1, 1/3, 0, 1, and 1, 3. That gives you a couple points to get your graph started. If you want to add more points to this t-chart, you can. If we add an x value of 2, we can add 1 more point on our graph. So here we have our graph. We do also have an asymptote at y equals 0. And you can sketch that in here. If we look at the next example, b of x equals 3 to the x minus 2. Our hk point is 0, -2, which is right here. Then again, if I use my t-chart up here, from this box, I'm going to go left 1 and up 1/3, over 0, up 1, to the right 1, up 3, and to the right 2, up 9. And there we have our graph. Here, our horizontal asymptote is at y equals -2. Exponentials always have a horizontal asymptote, and it will go through this hk starting point. For our next example, we have c of x equals -3 to the x. hk is 0, 0. The important thing on this function is to note that we have a negative out front. So this means that our a value, if we go back to our general form, is -1. And that is going to flip our graph upside down. So I'm going to rewrite our t-chart . Instead of our graph being here, it is going to get flipped over our horizontal asymptote. So our actual graph will be below our asymptote. And there we have our graph. Next, we have d of x equals 3 to the negative x. Our hk point is again 0, 0, which means our horizontal asymptote is at y equals 0. The important thing on this example is we have negative x. This is going to flip our graph over the y-axis. So instead of our graph being here, we're going to reflect it over the y-axis. And this will be our graph. Let's look at one more example. Here, we have g of x equals negative e to the x minus 3. Remember that e is approximately equal to 2.718. It is an irrational number, similar to pi, that is frequently found in nature. So if we are thinking about our t-chart, we're going to have 1 over e, 1, and e. So these are approximately equal to 0.368 and 2.718. Other than the base, all of the transformation rules are similar to what we just looked at. Our hk point is 3, 0. So our horizontal asymptote is going to be y equals 0. And since our a value is negative, our graph is going to flip upside down. So instead of our graph being negative 1, 1 over e, 0, 1, and 1 e, it's going to flip upside down. And be approximately this curve. Our domain for every exponential function is all real numbers. Our range for this graph, since it has flipped upside down, is negative infinity to 0. And our y-intercept, just like a y-intercept for any other function, we're going to plug 0 in for x. We get negative e to the negative 3, which is approximately equal to negative 0.0498.